with Mr. K. Mr. K here. This presentation is a study guide on the behavior of springs. This is a lead-in to the study of oscillations, otherwise known as simple harmonic motion, which is one of the fun things that springs can do. But first, we just have to learn about forces and energy with springs. So here we go. The main thing to understand at the start is that if you pull on a spring to stretch it, the spring will pull back, resisting the stretch. Rubber bands are like that too. The harder you pull, the more the spring stretches and the more the spring pulls back on you. The spring is, in a sense, opposing your attempt to stretch it. The spring tries to pull itself back to its natural length. Spring force is thus an example of what we call a restoring force. The spring force attempts to undo the change in length that you are imposing on it, restoring its length back to normal. You pulling the spring and the spring pulling back on you are parts of the same interaction. As Newton's third law says, these two sides to the same interaction are equal in strength and opposite in direction. We can call either one of these F sub S for spring force. Let's call the spring's natural undisturbed length L. When you pull on the spring, it stretches a certain distance. L changes. Let's call this change in length X. This is the traditional way it's done in physics books. The stretch length is thus L plus X. For most purposes, believe it or not, the length doesn't really matter. It's only the stretch X that matters. The harder you pull, the bigger the stretch, and the harder the spring pulls back. We can make a graph of this, spring force versus stretch. Often, for many kinds of materials, this graph is at least approximately linear. The slope of the graph is called the spring constant, abbreviated with lowercase k. A higher value of k means a stronger spring. If you look at this graph here, horizontally, we've got how much the spring is stretched. Vertically, we have how hard the spring is being pulled, which is the same in magnitude as how hard the spring is pulling back. And you see we have a nice linear graph with a slope, and again, that slope is k. The spring constant, which is an individual characteristic of each spring. It tells you how tough the spring is. A higher number is a tougher spring. The units for this are newtons per meter. A K of 1 Newton per meter would mean you'd only need 1 Newton of force to stretch the spring a whole meter. Most springs are a lot tougher than that. This idea is called Hooke's law, after the guy that discovered it, Robert Hooke, who was a contemporary of Isaac Newton back in the 1600s. Please note that this graph of spring force versus spring stretch is in y equals mx plus b form, with b, the intercept, being equal to 0, because if there's no force, there's no stretch. We can express this as an equation, as we traditionally do here in physics. Spring force equals k times x, with k being that spring constant, the slope of the graph. When you see Hooke's law quoted, such as in a textbook or on the College Board equation sheets that you get with the AP exam, there's often a negative sign included. Let's explain why. If you think of F sub S as how hard the spring pulls, then we need the negative sign. Why? Because the negative sign is for direction. The spring stretches in one direction, it pulls back in the opposite direction. K, of course, is the spring constant in newtons per meter. The negative sign is to say you pull the spring one way, but the spring pulls the other. The spring opposes the stretch. I said way more than I needed to. When you see Hooke's law quoted, such as on the equation sheet that a College Board gives you for the AP exam, there's often a negative sign included. Let's explain why. It depends on what you're thinking about. If you're thinking of that F sub S as how hard the spring is pulling, well then you need a negative sign for direction. The spring stretches in one direction, and pulls in the opposite direction, resisting the stretch. That's what the negative sign is there for. Don't let the negative sign confuse you. Whether to use it or not depends on how you are applying the Hooke's law equation. If you are thinking of F sub S as how hard is the spring pulling, then the negative sign is there to say that the spring pulls in the opposite direction as the stretch. But often we are thinking of F sub S as how hard is the spring being pulled. In that case, there's no negative sign because if you're pulling on the spring, you are pulling in the same direction as the stretch. Let's talk about the difference between real springs that you might encounter in the real world and ideal springs, such as you might encounter on an AP exam or in a made-up practice question. Real springs typically do not follow Hooke's law perfectly. It's usually necessary to apply a certain minimum force before the relationship between force and stretch becomes linear. This shows up on the graph as a sort of elbow at the start. Also, if you pull a real spring too much, you're going to damage it, and then it won't snap back to its original length, and that's called exceeding the elastic limit. Here in AP land, we generally deal with ideal springs, a kind of a model which assumes the spring is perfect. It follows Hooke's law precisely. There's no minimum applied force needed, so you get a straight line right from 0, 0, and it's impossible to damage the spring. Of course, this is an approximation in the same category as our frictionless surfaces and our ideal strings and our objects with fall through the air with no air resistance. Let's talk about a spring that is holding up a hanging mass. This can be a fast way to measure a spring constant. It relies on the concept of equilibrium. If you hang the mass from the spring and let the system come to rest, the mass will naturally hang at what we call the equilibrium position. This is the point where the downward pull of gravity, weight mg, is exactly canceled out by the upward pull from the spring force, which we know equals kx. So we can turn that into an equation. If we call the stretch at equilibrium this special distance x naught, we can say kx naught equals mg. Here is a quick example question. These are the kind that you need to get used to so that when you see them on an exam, you recognize it for the easy question that it is. A mass of 1.2 kilograms hangs at equilibrium from a spring with a spring constant of 40 newtons per meter. How far is the spring stretched? Well, this is a question about equilibrium position. Feel free to pause the video for a moment to try to solve this one on your own. Okay, the solution is just to set the spring force, Kx, equal to the weight, mg. Solve that for the position, you get x equals mg over k. Substitute the numbers, you get 1.2 times g equals 10 over 40. And in this particular example, the answer comes out to be 0.30 meters. In other words, 30 centimeters of stretch at equilibrium. Okay, here's a second quick example. What if we use the same spring and we doubled the mass to 2.4 kilograms? How would that change the equilibrium distance? Feel free to pause the video and work this out for yourself. Okay, the relationship between mass and stretch at equilibrium is simply linear. So if we double the mass, we're going to also double the stretch. Since the last question, the answer was 0.3 meters. In this time, it's going to be 0.6. Double the mass, double the stretch. It's just that simple. Let's think about the work done to stretch a spring. For an ideal spring, a graph of spring force versus stretch is linear with a slope of k. Think about it. This is a graph of force versus displacement. Like any graph of force versus displacement, the area under it equals work. The area represents the work done to stretch the spring to a distance x. This area represents the potential energy stored in the spring when it is stretched to a distance x. The work done to stretch a spring gets stored as potential energy in the spring. Potential energy that could come back out and do something like push something and make it move. This is one reason why springs are so useful and found in many machines. And it's also why springs are a common feature of physics exams, because they're such a great example of the storage of energy. Think about this graph. It's a triangle. The area under the graph is going to be 1/2 base times height. The base is x, the stretch. The height is the spring force, and we know that equals kx. So there's a big rectangle there whose area would be kx squared, and the triangle is only half of that area. So its area is 1/2 kx squared, and that's where we get this formula. The potential energy stored in a spring with a spring constant k when it is stretched to a distance x is U equals 1/2 kx squared. This is typically referred to as elastic potential energy to differentiate it from potential energy stored with gravity, which, as we all know, is U equals mgh. Make sure you memorize Hooke's law and this formula. So far, we have only talked about stretching a spring by pulling it to a longer length. It's also possible to squeeze a spring, compressing it to a smaller length. Well, everything we have said thus far about stretching a spring is also true of compressing a spring. Spring pushes back against the compression, resisting the change in length. Hooke's law applies. The potential energy formula is the same, U equals 1/2 kx squared. As before, if spring force is how hard the spring pushes, you need to put a negative sign in there to say that the spring is pushing in the opposite direction as the change in length. But if F sub s is how hard you are pushing on the spring to compress it, there's no need for a negative sign. Don't let this confuse you. It normally works itself out as common sense as you think about the questions when you face them. As a quick summary, here are the 3 key equations you need to know so far. Hooke's law says that for an ideal spring, the spring force, F sub s, is proportional to the spring constant, number that tells you how strong the spring is, times x, which is the change in length of the spring, whether the spring has been stretched or compressed. There's maybe a negative sign in there. It depends on whether F sub s is how hard the spring is pulling or how hard you are pulling on the spring. At equilibrium position, the spring force equals the weight of the mass hanging from the spring. So you have kx equals mg. You could solve that for any one of those variables. Here we've solved it for the stretch. And the potential energy stored in the spring is 1/2 kx squared. Equally true whether the spring is being stretched or compressed. We've covered the basics of the behavior of springs. It's time to apply these ideas. Let's talk about applying the law of conservation of energy to situations involving springs. This is super important for AP exams because the people that write those exams just love to put springs in conservation of energy situations. To review, the work done to stretch or compress a spring is stored as potential energy. This elastic potential energy, when the spring constant is K and the stretch or compression is a distance x, the potential energy is 1/2 kx squared. Let's look at an example of using the law of conservation of energy in a situation with springs. You might want to pause the video and read through this on your own, but here we go. A block of mass m is placed on a frictionless track, released from a height h, released with 0 velocity. Released means that at the bottom of the track, the block is going to hit an ideal spring with a spring constant of k. If you think what's going to happen in this collision, the kinetic energy of the block when it hits the spring is going to get transferred. The block is going to slow down as the spring pushes against it, and that kinetic energy will drop, eventually dropping all the way to 0 for an instant, while the potential energy in the spring builds up. At maximum compression, there will be an instant when the block is motionless and all of the energy is in the spring. After that, the spring will continue to push and the block will return to the left, but that's not part of this question. Here are the two questions. A, derive an expression for x in terms of the mass, the height, the spring constant, and physical constants, by which question writers mean g. And the second question gives you values for those quantities and asks you for a numerical value for the compression. Okay, let's look at this derive an expression question. On an AP exam, this type of question expects you to start from some kind of basic principle, second law, or in this case, they're looking for the law of conservation of energy. That's your starting point. They want you to show with logical mathematical steps how to arrive at this expression. You can pause the video if you want to try to work this out for yourself, or we'll just continue to talk through it. Note that this is a conservation of energy situation. The first step is to recognize that. How do we know? There's an exchange of position for speed. On the way down the ramp, you lose potential energy, you gain kinetic energy. And if the problem stopped there, we could compare potential at the top to kinetic at the bottom, as we've done in many other situations, and come up with the speed. However, the problem doesn't stop there. There's another exchange as the block hits the spring, and you get another exchange, and this time the speed going down as the potential energy goes up. As with all conservation of energy problems, the solution is going to depend on setting mechanical energy U plus K for one location equal to U plus K for some different location. We could, for example, choose the release point as one location and the instant before the block hits the spring as the other, and use this to find the speed of the block. However, that's not the most useful thing to do in this situation. This question doesn't actually ask us for the speed of the block, so there's no reason to take that extra step to find it. The question asks us about the compression of the spring, so we can go straight there. As we just talked about, the block's going to slow down when it hits the spring is going to get squished. Eventually, the block's going to stop for just an instant, and at that moment, all of the energy of the system, all of the mechanical energy will be stored as potential energy within the spring. Focusing on the question as asked, we need to find out how far the spring is compressed at maximum compression. The solution is going to be easiest if we compare the release point at the top of the hill to that instant of maximum compression, where the block has zero velocity and thus zero kinetic energy. Let's proceed with our derivation. The solution is going to be to set the potential energy to gravity equal to the potential energy stored in the spring at maximum compression. There's no kinetic energy at the start, and there's also no kinetic energy at the bottom when the block stops totally compressed against the spring. So it's basically U equals mgh at the top equals U equals 1/2 kx squared at the bottom. The rest is math, algebraic manipulation, and we come up with our answer. The maximum compression x equals the square root of the quantity 2 mgh over k. Having derived an expression for the maximum compression, we can then use that in question B. All we have to do is substitute the values into the expression we already have, do the math, and the answer comes out that the maximum compression of the spring is 1/2 meter. Here we have a second example. You might want to pause the video, read through this, try to make sense of it yourself, or we can continue to talk through it together. This is a throwback to Unit 1, a projectile motion problem involving a spring. AP exam writers love to do this, mix a little from here with a little from there. Here we have a compressed spring on a tabletop. The spring constant is K, the height is H, and there's a metal sphere of mass M that's pressed against the spring. The spring is compressed at distance x, but then it's going to be released, and the sphere is going to be launched horizontally. So this is a horizontally launched projectile problem, and we're given that it's going to land on the floor a horizontal distance r away from the base of the table. There are some values given for the quantities. The question really wants to know what's the spring constant k. If you wish, you can pause the video and try to solve this for yourself. or we can just talk through it together. Here, the potential energy in the spring will become the kinetic energy of the sphere at launch. We can analyze the projectile motion to find the initial velocity of the sphere at launch. And from that, we can use conservation of energy to find the spring constant. Let's look at the projectile motion. If you recall back from Unit 1, for a horizontally launched projectile, the time to fall is exactly the same as if you simply dropped the object from that height. We can use a kinematic equation for that, or we have our shortcuts that we developed way back when. Time to fall from a height h is the square root of the quantity 2h over g. Substituting the values in this question, we get that it's going to be a half a second of fall. And during that half a second of fall, the ball is going to be traveling forward with a constant horizontal velocity. Remember, in a projectile problem, the horizontal velocity never changes as long as we're ignoring air resistance. So it's going to travel 4 meters in half a second. So 4 meters in half a second, that's a velocity of 8 meters a second. That's the velocity of the sphere when it comes off of the spring. Now we get to the conservation of energy part of this. We know that the sphere comes off of the spring with a certain amount of kinetic energy, enough kinetic energy to give it a speed of 8 meters per second. So we could figure out how much that kinetic energy is. That kinetic energy would be the same as the potential energy stored in the spring before release. So we could work out the numbers that way, or we could do it in a slightly more elegant way by doing the algebra first. If we set the potential energy in the spring equal to the kinetic energy of the ball when it leaves the spring, we've got 1/2 kx squared equals 1/2 mv squared. Easy to cancel out the halves. Solve for k, because that's after all what the question is asking us for, and we get that k equals m times the speed squared over the compression squared. Substitute numbers, and we get a quite reasonable value for the spring constant, 160 newtons per meter. Okay, we've got one more example of conservation of energy. Example number 3. This time, let's continue with the spring shoots ball through the air theme, but this time we're going to do it vertically. A spring with a natural length of L and a spring constant K is housed in a vertical tube. The tube is the same length L. We've got a metal sphere of mass M placed on top of the spring, pushed down by some outside force, compressing the spring a distance x. When the force is removed, the spring is able to push the ball upward, and up it goes into the air, we presume. There's some values provided. The actual question is, what is h, the maximum height above the mouth of the tube reached by the sphere? You could stop and try this one yourself, or continue to the next slide and we'll talk through it together. In keeping with our theme, this is another conservation of energy problem, an exchange of position for speed, and we can solve this in 2 steps by first finding the potential energy in the spring, use that to find the speed of the sphere as it leaves the tube, and then we could use kinematics to find the height. There is a 1-step solution, but let's try this perhaps more natural 2-step solution first. This vertical situation has an extra wrinkle compared to the previous example problems, which dealt with springs placed horizontally. This sphere has elastic potential energy stored in the spring, but there's also gravitational potential energy in the Earth spring system. Thus, as the sphere begins to move upward, not all of that elastic U is going to become kinetic energy K. Some of the energy is going to go into lifting the sphere, increasing its gravitational potential energy. For gravitational potential energy, let's choose to put our height equals 0 line at the release point. That seems to be a sensible thing to do. And we can let that point be our position 1. Position 2 is going to be at the top of the tube, just as the sphere is leaving the spring, flying off into the air. So we've got U plus K at position 1 equals U plus K at position 2. Position 1 has no kinetic energy, no gravitational potential energy. All of the mechanical energy is in the spring, 1/2 kx squared. When the sphere gets to the top, position 2, the top of the tube that is, there's going to be some kinetic energy. It's going to be moving 1/2 mv squared. It will also have been lifted a certain distance, so there's going to be some gravitational potential energy, mgh. Now, if you think about it, the way this is set up, that gain in height in the tube is the same as the distance the spring was compressed. So h equals x here. That simplifies the math a little bit. The rest is algebraic razzle-dazzle, and we get the expression you see at the bottom of the screen here. Well, we've done the physics and part of the math. The rest of the math is substitution and coming up with an answer. We come up with the square of the speed as the sphere leaves the tube is 45. So the speed is the square root of 45. Now, I could work that out as a decimal, but I've been down this road before, so I'm going to just leave it as the square root of 45 until we get to the next slide. So now we have the speed of the ball as it leaves the tube, the square root of 45. It's going to continue up and gain height. From here, we can use kinematics. We've got the equation that we always use when we don't know and don't care to know the time, twice the acceleration, which is g, times the change in position, which is h, equals the final velocity squared, that's going to be 0, minus the initial velocity squared. And that's going to be the square of the square root of 45, which is why we didn't bother working out the decimal before. We're just going to square that square root. A long time ago in Unit 1, we worked out shortcuts for these kind of things, and the relationship between the height gained based on the initial velocity in the vertical direction is the height is that initial velocity squared over 2g. Pop in the numbers, and we get that the height gained by this thing above the mouth of the tube is 2.25 meters. Problem solved. Now, that is a solution to this, and it follows a certain logic, and it's probably one that many students are comfortable with. However, there is a faster one-step solution that a very experienced student would probably do instead of what we just did. The one-step solution is to not bother finding the velocity. After all, the question doesn't ask for that. Let's directly relate the start position when the spring is compressed to the final position when the sphere is way up in the air at a height h above the tube. We can let position 1 be that release point when the spring is compressed, and position 2, that moment of maximum height. And for this, we might want to make a slightly different choice about where to measure the height. We could keep it where it was, everything will work out fine, but it'll be a little bit simpler algebraically. Since we want to know the height above the tube, let's measure h equals 0 from the mouth of the tube. This means that the sphere will originally be below that line with negative gravitational potential energy, but that's perfectly fine. There's nothing wrong with having negative gravitational potential energy. It all depends on your frame of reference. All right, down there at position 1, at the release point, all of our energy is potential energy. There's no motion yet. We've got potential energy stored in the spring, 1/2 kx squared, and we've got potential energy due to gravity. Now that's mg times our height, but our height here is a distance x below h equals 0, so it's negative gravitational energy equal to mgx. All right, at the very top of the flight, up there at that maximum height h, no potential energy in the spring, no kinetic energy, everything is gravitational potential energy, mgh, h being the height above our 0 line, which we put at the top of the tube. Now we do some algebra, we pop in our numbers, and we end up, the height is indeed the same answer we got before, 2¼ meters above the top of the tube. It's often a good idea to stop and think about answers after you get them. Look at the form of this. The height came out to be 2½ meters minus 1/4 meter. What is this? This is the sphere's maximum height is 2½ meters above the release point, and that's 2¼ meters above the top of the tube. One last word about this situation. This is real thinking like a physicist territory. Let's look at that expression that we got for maximum height before we put the numbers in it. There's 2 terms there, and there's a minus sign in between them. that means there's room for these two terms to cancel out. We could even get a negative result, which would mean our height would be too short to get out of the tube. Well, this is actually natural if you stop and think about it. The spring has to be strong enough to shoot this sphere all the way out of the tube. And M has to be small enough that that can happen. If you've got a very heavy weight and a weak spring, it might be that this launcher doesn't even work. The sphere never gets out of the tube. And that's right there in the math. There's just one more part of this topic we need to cover before we leave this introduction to springs, and that is spring combinations. What if there's more than one spring and the springs are connected to each other? How does that work? Okay, to look at spring combinations, let's look at the simplest case, just two springs connected to each other. Logically, there's two ways you could accomplish this. You could have the two springs side by side, they're connected at both ends, or you could have one spring after another, only connected in the middle. That first way, connected at both ends, we call a parallel combo, and the other way, where there's just one connection in the middle, we call that a series combination, one spring after the other. All right, let's try to simplify this because we've been at this for a while. Let's cut to the chase. For both of these combinations, there is a pretty simple formula that you can use to come up with what's called the equivalent spring constant. Let's take a look at that parallel combination on the left. Essentially, what you want to do here is mentally imagine replacing those two springs with a single spring that would have the same characteristics. It would take the same amount of force to stretch it by the same amount. Well, if you think about stretching those two springs, the fact that there's two springs is going to make it harder. You're going to have to pull harder to stretch both springs. The combination is stronger, and it works out very simply mathematically. If you could imagine replacing those two springs with a single spring, the equivalent spring constant of the single spring is simply what you get when you add up the spring constants of the individual springs. K equivalent equals K1 plus K2. Let's look at the series combination on the right side of the screen. Everything here is going to be sort of flipped from the parallel combo. For a series combo, you pull on the end of one spring and that force gets transferred along the line, and it also pulls on the second spring. You stretch both of them for the price of one force. That single mass at the bottom is going to stretch both springs. And that makes the whole combination stretch more than either of the individual springs alone. So thinking of replacing this combination with a single imaginary equivalent spring, that equivalent spring would be weaker than either of the individual ones. For the parallel combo, the combination is stronger than the individual springs. For a series combo, the combination is weaker. And there is a mathematical way to find the equivalent spring constant of a single spring that could replace the combination. It's a little trickier than the simple add them up formula for parallel. You do just add them up, but you don't just add them up. You add the reciprocals, and what you get is the reciprocal of the equivalent spring constant. 1 over the equivalent spring constant equals 1 over the first spring constant plus 1 over the second spring constant. In practice, if you only have two springs, which is probably all you're ever going to face, the simple way to do it, I can show you mathematically that this works out, or simply accept it, is the formula that's at the bottom of the page there on the right. It's the product of the two spring constants divided by the sum of the spring constants. This works, as we'll see in the next slides. Okay, the next few slides are going to be proofs of these formulas that I just gave you. And the first one here is a proof of where that formula comes from for the equivalent spring constant of a parallel combination of springs. I am not going to talk through it. I invite you to read through it yourself if you're interested, or simply make sure that you know and can use the solution, which is that the equivalent spring constant is the sum of the two individual spring constants. And here we have the proof of the formulas for a series combination of springs. Again, I'm not going to talk the way through this. I don't think there's much point in that, but you are welcome to pause the video and look through it yourself. Or you can simply accept the conclusion. The formulas that we have already given, if you need to find the equivalent spring constant of a series combination, you can add the reciprocals and then take the reciprocal of that result, or you can use that shortcut formula of the product over the sum. Here we see the rest of the math steps involved in deriving that formula for the equivalent spring constant of a series set of springs. You can read through at your leisure or continue on to the next slide. And lastly, with this proof for a series combination of springs, here is how we can go from that reciprocal-based formula to the shortcut that only applies in the case of two springs, but it's a very convenient shortcut. The product of the spring constants divided by the sum of the spring constants will give you that equivalent spring constant. And here is a review of the bottom line of all of those derivations. The formulas that you can use to find the equivalent spring constant for a parallel combo and for a series combo. What if the springs have the same spring constant, identical springs? This is important because College Board doesn't really try to write tedious, complicated questions. They often prefer to write a question that the math is simple. It's the concept that they want to see if you know. And in this case, they want to see if you know that a parallel combination is stronger than the individual springs and a series combination is weaker. What if the springs are identical? For the parallel combo, two springs simply gets twice as strong. The equivalent spring constant is twice the spring constant of the individual springs. For the series combo, it's the other way. The combination is weaker. So if the springs each have a spring constant of K, the combination will have an equivalent spring constant of 1/2 K. Before we end this, let's try one example. Suppose we have two springs. One has a spring constant of 10 newtons per meter and the other 30 newtons per meter. What would be the equivalent spring constants if we connected these guys in parallel and if we connected them in series? Feel free to pause the video and try to work this out yourself. We will continue in just a moment. In parallel, the combination is going to be stronger than each of the individual springs. All we have to do is add up the spring constants to find the equivalent. 10 plus 30 is 40 newtons per meter. That's it. For the series combination, we have our reciprocal-based equation. The reciprocal of the equivalent spring constant is going to be 1/10 plus 1/30. Now that's the same as 3/30 plus 1/30, or a total of 4/30. So the reciprocal of the spring constant equivalent is going to be 4/30. Flip it, and the equivalent spring constant is 30/4, which is 7.5 newtons per meter. Let's look at our shortcut for this situation, the product over the sum. The product is 10 times 30. The sum is 10 plus 30. That's 300/40, which is the same as 30/4, which is 7.5 newtons per meter, the same equivalent spring constant that we came up with the reciprocal method. By now, we've talked about, and you should know a little bit about, Hooke's law, the idea that spring force is proportional to the change in length of the spring. Spring force is a restoring force opposing the change in length. We have a spring constant, K, which represents the stiffness of the spring. A higher K means it's harder to stretch or compress that spring. Either way, if you do stretch or compress a spring, you are storing potential energy in the spring as you do that work. And the amount of work done equals the amount of potential energy stored, which is 1/2 kx squared. If you hang a mass from the bottom of a spring, it's going to naturally come to rest at a point where the spring force is exactly enough to cancel out the weight. That is kx equals mg. We can use conservation of mechanical energy in situations involving springs, as we have seen through our examples. And we can also talk about combinations of springs, whether parallel, where the combination is stronger than the individual springs, or series, where the combination is weaker than the individual springs. This has been a lot to talk about, but it's been quite a thorough explanation of the basics of how springs work. For our next step, we're going to talk about what happens if you shake things up. What if you have, for example, a hanging weight from a spring, but it's not at the equilibrium position? What if you pull it down below and let go? Well, exciting things happen, and we'll talk about that in our next go round. Thank you very much.